artificial intelligence. As many artificial intelligence systems continue to evolve and expand their capabilities, their capacity to acquire, process, and utilize vast amounts of information becomes increasingly essential. With this knowledge, AI systems are empowered to make more accurate predictions, solve complex problems, and in complex problems and enhance our understanding of the world around us. Moreover, this synergy between the AI and human intelligence has the potential to propel the human progress to some new heights, and it enables us to harness the power of the knowledge in the ways previously unimaginable. And and the neural knowledge and the symbolic knowledge represent two distinct yet complementary approaches to representing and processing information in the field of artificial intelligence. And neural knowledge is primarily derived from the data-driven learning process, such as those empowered by deep learning algorithms and neural networks. And these systems excel at tasks like pattern recognition and natural language processing, image classification, by extracting some implicit, implicit knowledge from vast amounts of data, enable them to make predictions and adapt to new information. And on the other hand, symbolic knowledge refers to the explicit representation of the knowledge in a structured and human readable format, such as rules, facts, and relationships. And symbolic AI, often associated with classical AI, empowers techniques like logical reasoning, knowledge representation, and expert technologies like to manipulate symbols and perform high-level cognitive tasks such as planning, problem solving, and inference. And by harnessing the strengths of both neural and symbolic knowledge, researchers can be aim to develop hybrid AI systems that can leverage the robust learning capabilities of neural networks while also benefiting from the interpretive and generalization offered by the symbolic knowledge like knowledge graphs. And this holistic approach has the potential to unlock the new levels of intelligence and understanding, paving the way for more advanced and versatile and human-like AI systems. Okay, to build the knowledge graph, we need to extract the entities and relations from the unstructured data. For example, the model has to extract the entity Jack and Dr. Jim from the sentence, and the model also has to extract the relation it spouts off from the sentence given the entity Jack and Dr. Jim. Then the model can extract the relational triple Jack is spouse of Dr. Jin to build the knowledge graph. To train the to train the knowledge graph construction model, we have to leverage a large scale of labeled data to fine tune the model, which is also labor intensive. Specifically, it is very challenging to annotate the data in some vertical domains such as biomedical and also many vertical domains. So to address the label intensive issue, recent decades have witnessed the fast development of the prompt learning, which is an emerging approach in artificial intelligence and machine learning that focus on quickly adapting to new tasks or problems based on a limited number of examples or guidance. And unlike traditional machine learning methods, which often requires a very large amount of data and expensive training, and the prompt learning aims to achieve very rapid generalization and problem-solving capabilities using minimal input, just like a prompt. Like here, here's an example of the machine translation prompt, translate English to French, cheese, and then with such a prompt, the model can uh, have the ability to make the machine translation. However, for the knowledge graph construction tasks, such as relation extraction, there are still two major issues. The first issue is the prompt design with complex semantics. The relation labels of per country of birth and organization city of headquarters cannot specify a single suitable label word in the vocabulary. And the second issue is the inductive bias for knowledge graph. So if a pair of entities contains the semantics of person and country, the prediction probability of the masks on the relation organization city of headquarters will be very lower. Okay, so to address this issue, our team we propose a very simple approach called no prompt, which utilize virtual embeddings as an alternative to entities and relation types. Here is the virtual embeddings of uh, relations, and here is virtual embeddings of the entities. We further construct the prior structural constraints on the entity and the relations for the no prompt. That's a very simple idea because the entity types can constrain the relation type. And then we evaluate the proposed approach on several benchmark datasets, which demonstrate the effectiveness of the proposed no prompt. And as you know, you can see that the model can obtain some better performance. And we also first evaluate the no prompt in low resource setting, few shot setting. We noticed that the no prompt can obtain better performance in few shot settings like 8 shot or 16 shot, which means we only have eight, 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 eight instance per region per class. And the code is available at here. And so if you want to try the no prompt, you can just download the code and have a try. And we further evaluate no prompt on a low resource relation extraction benchmark, which is recently accepted by SEMP findings. It has 8 datasets of a single sentence and document with various languages, including Chinese and English languages. And we find that no prompt can obtain better performance on most datasets, but fails on several vertical domain settings such as science. Here is science and science and some medical domain, which indicates that the vertical domains are very challenging for relation extraction. And we also obtain some interesting findings such as data augmentation can even obtain more performance gains than prompt learning for some data sets. And since the embeddings of the prompt are learned in continuous space, it is very intuitive to explore what precisely the optimized prompt or verbalizer is. So we use Disney normalization to visualize the embeddings. We also get the top 3 token nearest the virtual answer words. It reveals that the virtual answer words learned in vocabulary space are semantic and intuitive. However, when conducting more experiments and case studies, we also noticed that no prompt fail on some extreme low resource settings such as 1 shot and 3 shot, or generalized poorly on some new domain. So to address this issue, after finishing his work, no prompt, we makes a deep thinking. We think it is non-trivial for parametric models to learn rare or hard patterns well with rote memorization, uh, uh, thus it resulting in inefficient generalization performance. Uh, in other words, we want to argue that it is no need to memorize all knowledge in the parametric space. Moreover, recent studies have proposed a long tail theory, which noticed that when the training set has a long tail distribution and contains small subpopulations and with ethical instances, then pre-trained language models indeed predict on the test set data through the rote memorization these ethical instances rather than learning the common patterns. So, we would like to mention that the limitation of the rote memorization for neural networks remind us the human learning of process of learn by analogies, or the proverb that the palest ink is better than the best memory. So motivated by this, we try to improve the generalization ability of prompt learning with retrieval and association. And our intuition is that the difficulty of resolving the above limitations can be substantially alleviated if we can decouple the knowledge from the memorization. Okay, so we introduce a very simple idea of retrieval augmented prompt learning. We call this retro prompt, which is extension of the no prompt as shown in this figure. And the open book knowledge store with keys and values are defined as the set of prompt-based example embeddings and the corresponding label words constructed from the training data, which are served as additional references. And we also designed to incorporate the neural demonstrations, which is several in-context examples into the input sequences as the in-context augmentation, where the demonstration is retrieved from the knowledge store. And then we apply a non-parametric algorithm KN over the input query and the knowledge store, and regard KN results as an indication of easy versus hard instances. And moreover, we automatically force the model to emphasize the hard instances identified by KNN by assigning a scaling during the training. And we evaluated the retro prompt on several benchmark datasets of few shot and zero shot learning to demonstrate that the retro prompt can obtain several better performance than baselines like LM, and no prompt. And the code is also available on GitHub. And after after finishing this job, we all further try to notice that the schema knowledge is also very important for the knowledge graph construction. And we then finally propose a new approach of dynamically generate the prompts for knowledge graph construction based on schema knowledge, which is called RAP. This approach generates the prompt based on the schema knowledge, which indicates that the schema such as the entity type and the relation type, the entity and the relation constraints are very important for the prompt design. And we generate those prompts dynamically based on the schema knowledge, and which is the dynamic retrieval augmentation framework. And we find that those schema knowledge is very important for the efficient, data efficient knowledge graph construction tasks such as relational triple extraction and event extraction. And this work is also accepted by CGR 2023, and the code is also available online. And if you have any questions, you can find the code and the data. Okay. I will further introduce the knowledge construction with large language models such as GPT-3. Since all these previous mentioned works are utilize language models like Robota and T5, and so it is very intuitive to analyze how can we use GPT-3 or ChatGPT to build the knowledge graph. And to be noted, and all those previous works I mentioned, like no prompt, retro prompt, and RAP, utilize those small language models. They have to tune the parameters. Uh, we introduce a new work of how to unleash the power of large language models for few short relation extraction. We provide a very simple empirical study using in-context learning and data augmentation for with GPT-3 for ratio extraction. And empirically, we find some very interesting conclusions and empirical findings, such as the in-context learning cannot obtain very well performance than the fully supervised learning methods. And we also find that the data augmentation, data generation from the GPT-3 can significantly boost the performance. Here is a figure which shows that how we can generate data based on GPT-3. We can use some schema constraints also. We can use some entity types and region types as constraints. Also, we can use this schema constraints to generate the instance for region extraction, and then we can use those generated data for training, and this can result in a very significant performance improvement. And another similar work by NTU observes that when the data is very scarce or also one shot, large language models may perform better. And when the data increases to around 10 shot, the performance of large language model is very limited. And in datasets with many labels, large language models may lose their advantages even in one-shot scenarios, such as in this Marvin dataset. Here's performance result for region extraction in Marvin. And large language models have issues with high latency and high cost. That's a major issue for using large language models to generate or construct knowledge graphs. And moreover, we further evaluate the performance of GPT-4 and ChatGPT for knowledge graph construction, and we find that the performance of the GPT-4 is still weaker than the fully supervised small language models. We evaluate on several datasets, and we find that using GPT-4 or ChatGPT with in-context learning, the model cannot obtain the best performance than the fully supervised learning. And but we also notice that GPT-4 has a very strong generalization ability, which can extract new and more complex knowledge and can continually improve the performance through the observation of the input instructions. In other words, we can use prompt engineering. We can use several well-defined prompts and instructions to improve the performance of using ChatGPT and GPT-4 to construct knowledge or information, extract entities and extract regions, extract events, and that's a very amazing findings. Okay, and to conclude, in this talk, we can find that directly pumping the large language models currently relies on prompts, and in one sentence, the performance is still not satisfactory with in-context learning for GPT-3 and ChatGPT, GPT-4, and moreover, it is also related to the indicator of the generated model, and it is not easy to evaluate the quality as good or bad. For example, we use ChatGPT and GPT-4 to generate the triples, but we usually find that those triples are not the same, are not in the same format in the original dataset. So it is very difficult to evaluate the performance in such a situation. So we think it is also very important to design some new evaluation metrics for using large language models for knowledge graph construction and information extraction. And besides, that's the last finding is we using large language models for data augmentation is a very powerful solution for knowledge graph construction. We can use ChatGPT, GPT-4 as data augmentation to generate more data for training the knowledge graph construction model, like entity like name entity recognition, region extraction, and so on. So to better utilize the large language models, recently our group developed several tools such as the Easy Instruct. This is a very simple tool to better utilize large language models for knowledge graph construction. It is very simple for usage. Just a pipe install Easy Instruct, and this toolkit is still fast developing. So you can just download the GitHub, the source code of GitHub from GitHub, and you can try to use the tool. Here is an example of how to use the tool. You just set the OpenAI key, and you can declare a prompt class like base prompt, or in context learning prompt, or information extraction prompt, or chain of thought prompt, or index prompt, or you can use some multimodal prompt, or you can use some batch prompt, which indicates that we can query several batch for the OpenAI for the OpenAI ChatGPT and GPT-4. So we designed this easy constructor for easy to extend and multitasking and efficient. If you want to try, you can just try the easy instructor. And if you have any questions, you can just pull some issues, and we will answer your questions as soon as possible. And here are also some other toolkits. And we also developed Lambda KG and Delta KG. Here, the Lambda KG is a library for knowledge graph construction that equips with pre-trained language models and supports various tasks such as knowledge graph link prediction, question answering, and using knowledge graph to recommendation, and also knowledge graph probing tasks. We support we support many large language models and also small language models such as GPT-3, ChatGPT, and KGT5, and generator KG knowledge graph construction, and also KG Bird and Star, which utilize the robot and bird for knowledge graph construction. And interestingly, we also provide Delta KG, which is a library for editing pre-trained language model based knowledge graph embeddings. If you want to use these tools, just have a try. And these toolkits are still fast developing, and we will add new functions and new abilities in the next few months. And these toolkits can support a large language model or language model based knowledge graph representation and applications. Okay, finally, in the large language model area, we should construct. There's a big change in the large language model area. We should construct the knowledge graph from or based on large language models, and utilizing knowledge graph to enhance the large language model. Of when to utilize neural knowledge based on some specific applications. Because in some specific domains, there are many well-defined symbolic knowledge, and also these data are very the data the data are contain some privacy issues, and we have to put those data in our private server. So in such a situation, we can better. It is also better to utilize those symbolic knowledge for knowledge graph construction and applications. But in some general domains, there are many unstructured data or text corpus, so we can just build a large language model to represent all those knowledge, and it is very intuitive to use the large language models to represent those general knowledge. And so in such a situation, the neural knowledge is more important. Okay, and at the end of the talk, I would like to thank all those members in my team. And we are a research group devoted to innovations in the field of knowledge graph, natural language processing technologies, and graph learning. And thank you, thank you again. If you have any questions, feel free to contact me via the emails. Sorry, I got a COVID-19, so it is sorry again for the inconvenience during my presentation. Thank you.